Welcome to our presentation. Our project is called Surfside Science, and we are a team of experts and students with expertise in science, technology, engineering, mathematics, and arts. We are developing and testing several methods for environmental monitoring, focusing on satellite imagery and low-cost electronic sensors. The objective of this project is to contribute to the increased resilience of Aruba's marine and coastal ecosystem to the impacts of climate change. This project seeks to validate low-cost methods to measure coastal, marine, and land-based environmental parameters and improve access to reliable data. Aruba, like many other small island development states, lacks baseline data, including continuous measurement of the state of several environmental indicators. By validating low-cost replicable monitoring tools, we can increase monitoring capacity and thereby have better understanding and earlier warnings of marine and coastal ecosystems. Environmental parameters. At our pilot site of Surfside, we'll be measuring the following parameters. For air quality, we'll be measuring particulate matter in the sizes of PM1, PM2.5, and PM10. These are the particulate sizes in micrograms, and we will be measuring them in micrograms per cubic meter. And besides that, we also measure humidity and temperature. And now, for the water quality, we'll be measuring the water pH, dissolved oxygen, temperature, and electrical conductivity. And for the coastal change monitoring, we'll be monitoring the vegetative cover, coastline, size of reef islets. And for the seafloor mapping, we'll be monitoring the seafloor cover, including shallow reef and aquatic vegetation. Replicable methods. This requires low-cost hardware, so most people can afford it. Accurate sensors for data reliability. Open source software, so there's a lot of transparent and widely available documentation online. And accessibility. Components should be widely available. Air and water quality. Air quality monitoring. For the sensors, we decided to go with a PMS 5003 particulate matter sensor and with the SPS 30, which is also a particulate matter sensor. And for temperature and humidity, we decided to go with the Adafruit SHT 31 sensor. As you can see, I already mentioned the parameters. The particulates we measure from PM1 to PM2.5 and PM10 micrograms per cubic meter, and temperature in Celsius, humidity and relative humidity in percentage. And for the data pipeline, how it works is we collect 5 samples per hour. We get the average and we check for the range if they're in the correct ranges, minimum and maximum ranges. And the way we send it to the database is in a form of JSON, where we contain the value, the unit, timestamp, the sensor ID, and also the station ID. Water quality monitoring. For the sensors, we chose to go with the Atlas Scientific sensors, which include the lab grade pH probe, conductivity probe K1.0, lab grade dissolved oxygen probe, PT1000 temperature probe. For the parameters, these include acidity in pH, dissolved oxygen in milligrams per liter, temperature in degrees Celsius, conductivity salinity in microsiemens per centimeter. And now for the data pipeline, it works exactly the same as the air quality one. We collect 5 samples per hour, get the average, make sure they're in the ranges, correct ranges, and then we send in a form of JSON to the database, where we include the values, unit, timestamp, station ID, and also sensor ID. Hardware. As you can see, there's 2 wiring diagrams, one for air quality and one for water quality. What these two have in common is they're development boards. As you can see, they both use the same one, and this served as an ideal choice for environmental monitoring systems due to its comprehensive built-in components, minimizing the need for extensive soldering and simplifying our component list. The air quality uses a SHT31 sensor, which is connected via I2C to the ReallyGo, and 2 PMS 5003s, which are connected via UART pins to the ReallyGo. And the SPS 30, there's an extra slot for it for future development, which is connected via I2C to the LilyGo. And besides that, you can also see there's a buck boost converter. In here, we use the boost to boost the 3.3 volts to 5, so it can power the particulate matter sensors. And there's also a 5V solar panel connected for self-sustainability. For the water quality monitoring system, we integrated an array of sensors, including ESO dissolved oxygen, RTD, temperature, conductivity, and pH sensor, all linked to the board via I2C GPIO pins. And to ensure accurate readings, an ESO voltage isolator was incorporated to isolate each ESO circuit, which can be seen here in purple. Must note that the water quality monitoring system uses the same components as the air quality monitoring system, except for the PM sensors, the SHT31, the buck boost, and the buck boost converter. Only the distinct components are shown in this wiring diagram, but the water quality also uses this solar panel and also these capacitors resistors, and transistors. To streamline our project, we designed a dedicated PCB board for both air and water quality monitoring systems. These PCB files are compatible with online PCB manufacturing services, simplifying the process of creating the necessary circuit boards. And here you can see a 3D view of how that might look. Software. The air quality and water quality monitoring systems both follow a consistent software sequence. It begins with the ESP32 waking up from sleep, creating sensor objects, and implementing a 10-minute watchdog timer to allow for throw checks in case of issues before resource cleanup. In the enable state, sensors are enabled calibrated. Next, in the sample state, data from sensors is sampled 5 times, followed by network connection establishment, data posting to the database, and modem deactivation. Simultaneously, sampled data is written to the SD card, and any errors are logged in the SD card. If errors occur in any state, they are recorded in the SD card. Before transitioning to the sleep state, the watchdog timer is disabled. The ESP32 then enters a 1-hour sleep mode to conserve energy. Air quality validation. Our air quality monitoring system was tested against the air quality particulate monitor, which is a high-end standardized device for measuring particulates. This was done for 24 hours to determine accuracy. Field validation was done against replicates to determine the accuracy of replicability. And also, field data analysis was done to determine temporal drift, and multivariate analysis was done to determine influence of temperature, humidity, and particulate matter measurements, because in some cases, some humidity droplets may be confused for particulates. For verification, unusual events were troubleshooted by a process of identifying and flagging outliers, determining the causes of the outliers, determining the validity of the data points, and cleaning the data where appropriate. And for statistical analysis in RStudio, 9 set of performance measures were done. Water quality validation. Lab validation was done using artificial seawater. This solution was used to confirm expected ranges. Our air quality monitoring system prototype was tested against the HM500 Hydromaster, which is a high-end standardized water quality monitoring system. This was done for 24 hours to determine accuracy. Also, field validation was done against our replicates to determine their quality. Also, field data analysis was done to determine temporal drift. Multivariate analysis is done to determine influence of temperature on water quality measurements. And external water sample audits was done for conductivity and pH. Furthermore, pH validation was done in local laboratory using spectrophotometry verification. Usual events will be troubleshooted by a process of identifying and flagging outliers, determining the cause of the outliers, determining the validity of the data points, and cleaning the data where appropriate. Statistical analysis was done in RStudio, which included a set of 9 performance measures. Conclusions. For the air quality, the PM measurements are comparable with the Gaia used by World Air Quality Index, and the PM 2.5 values are within similar range as other high-end sensors. High variability and overall consistency, slightly higher values compared to the other high-end sensors. And for the water quality, pH measurements were not reliable and are therefore not used, but the temperature and absolute conductivity of the oxygen demand are all measured in a similar range as high-end sensors, but with higher variability than reference meters.
Seafloor mapping with branchies and scubble bubbles. Here we gear up to dive into underwater mapping, preparing, and testing. My role was to capture seafloor pictures while the dive master navigates with a compass, coordinating with the swimmer holding the GPS. Long dives, tricky channels, but happy contributing to vital research.
Coastal change mapping. Our approach to coastal mapping in the Surfside Beach region integrates the knowledge of GIS applied to satellite images using Google Earth Engine. Here we measure the reef islands and the coastline. To map the coastal vegetation, we use the NDVI, which is an indicator of health and density of vegetation along the coastline. For the reef islands and coastline delineation, we use NDWI, which assists in the accurate delineation of reef islands and identification of coastline borders. For the shoreline shallow marine habitats, we employ supervised learning to identify and categorize these areas. And our adaptable code can easily be customizable to accommodate various regions and satellite datasets, making our approach versatile and scalable. The goal with AI seafloor mapping was to create a map of underwater vegetation in the Surfside area. Here we collected underwater images with a kayak and a GoPro to be analyzed using machine learning algorithms. The kayak-derived images were collected and put together like a puzzle to create a non-comprehensive map. And the images that were collected, they were added into our Zooniverse project for labeling, where people could identify the seafloor elements within the images, such as sand, corals, rocks, rubble, seagrass, seaweed. The label images were then used to train a machine learning model to automatically process the images. And here we can see what percentage of Surfside Beach is composed of vegetation and corals. And in the long term, we can measure changes in the future, whether it becomes more, less, or it stays the same. The validation of the AI seafloor mapping. So for our test, the satellite-based AI can analyze entire areas in minutes. What was done to validate the AI model was determining the accuracy of the image classification by comparing them against with classifications of experts. So when looking at the classifications, our AI needs better accuracy. Our system demonstrated a testing accuracy of 81%, and this was evaluated through a rigorous testing process, which involved assessing the system's ability to classify seafloor data. And the validation accuracy stood at around 20%. And we used like the performance using the ground observation, but we limited the data points within 5 meters post of challenge. So for the conclusion, despite the high testing accuracy, we acknowledge we need to gather more testing data to further validate our results. And our validation accuracy underscored the need for improving the accuracy of the ground observation and addressing potential GPS-based errors affecting both the AI model and the ground truthing process. Our data portal So for our data portal, we Surfside Science developed a comprehensive database covering all the right environmental aspects such as the air quality, water quality, seafloor conditions, vegetation, coastline data, and the information about the reef islands. The portal itself is accessible from our website, science.branchespoint.com, and it's really to access the data, you can just simply select your desired time frame, specify your area of interest, and choose the parameters relevant to that area. The portal itself will give you the available data for download in CVS format, which you can use for your further research or endeavors. If you want, thank you for listening. If you want to read or keep updated about our project, please look at the website science.branchespoint.com. Yes, thank you.